All right, finish this up. We'll talk about the hyperbola. Now this is a set of all points relative to two fixed points, point here and here. Set of all points for which the distance from these 2 points, let's say D1 and D2, the difference, D1 minus D2, the absolute value. In other words, I could do the same thing for D2 minus D1. That distance is constant. Okay. Now, if under those conditions, what you'll have, the way I've drawn this one, is you'll have a center between the two foci, 1 and 2, we'll call those, and your curve will look something like this. And over here, something like that. And there are parts here that we can talk about. This is the transverse axis here, from this point to this point, transverse axis. Okay. And this connects two points that we would still call the vertices, here and here. Okay, so you got a transverse axis, and it's from the center. The distance from the vertex to the center is still A. Okay, still A. And the distance from the center over to this focus is also C. Okay, remember that same relationship back in the ellipse, from the center out to the focus was C. But you notice in this case that the focus is outside of, in a sense, outside of the ellipse. So depending on where that focus is, you end up with either an ellipse, or you could say either an ellipse or this hyperbola, depending on where it is. So there's probably some neat software that you can use, where you can just drag that focus back and forth and watch how this turns from an ellipse into a hyperbola, going back and forth. But anyway, okay, so using this idea and the distance formula now, because there are certain things that are true about this. D1 plus D2, if you find these distances down here and you analyze them as the point moves down the curve, if it hits one of these vertex, there's vertices here, if it hits a vertex, then D1 plus D2 actually turns out to be a constant 2A again, just like with the ellipse, if you remember. And from there, I'm sorry, not D1 plus D2, that's the D, that was the D difference in there, not D1 plus D2, it was this thing. The D1, not that absolute value in there. Okay, so that turns out to be our constant in this case. Sorry, that's not right. It is the D1 minus D2. I don't know what I was thinking. Okay, so as I said, that's a minus in there. It can also be D2 minus D1 like that. It's also equal to the 2A. But in any case, if you begin with this, you can start with the positive one. We'll also take the D2. We'll just assume d2 minus d1 is positive. It doesn't really matter. It'll be a constant. From here, you can build by finding these distances d1 and d2. This would be the case where you had a positive. D2 was bigger than D1. Okay. I mean, you don't have to be too careful about that because you are. Okay. So just to clear that up, let's see. Just to clear that up, you could. I mean, I named these arbitrarily up here anyway, so you could say that's D2 and that's D1 if you're going to be a stickler about the size of these. 1, come on, and 2. Okay, and that way you know it'll be positive. D2 will be bigger. And now the reason we have 2 branches is because the way I've drawn it here, this produces one locus of points by assuming D2 is bigger than D1. But if it were the other way around, you would end up with another set of points coming around this way. So that's why I've drawn both of them in here. Okay, both sets. And this would be, if you switch this back the other way, then you would have this distance over coming across here and the distance in here. Okay, so you'd have labeling these either D1 or D2, depending on which one is bigger. You could then state the same thing here. Okay, anyway, by using the distance formula, you can work this down, and there is an assumption along the way, a simplification, that basically we do a substitution and we let b squared equal to c squared minus a squared. Okay, where the a and the c are these numbers that I have up here. C is the distance from the center out to the focus, and a is from the center to the vertex. So if you make this as a substitution using distance formula and a good amount of algebra, with this substitution, you will end up with, and the one we have here, the orientation that we have here, you'll end up with this. All right, so that's our first one here. Now this one has the center translated from to HK, but it's the same form otherwise. And this one has the transverse axis turned the other way. So instead of along the transverse along the x direction, you have parallel to the y-axis. So now, before we get started on an example, I just wanted to say something else about this one. There's a relationship that we're going to use to help us draw these things. And it comes from, let's see, it comes from the fact that if you start working with this equation here, let's assume that the center is right at the origin, just for simplicity's sake. And then come around, solve this for the y. So in other words, you're going to work with this thing. Solve this for y. So you have this. So we bring that over, and then it's b squared times. And then y would be equal to, technically speaking, plus or minus b, and then the square root of x squared over a squared minus 1. Now, if you look at the limiting behavior of this expression, what happens as x goes to infinity? You'll notice inside here, The -1 doesn't really affect much when x is large. So you really just have y being equal, heading to plus or minus b over a times an x. With this kind of behavior, this is known as asymptotic behavior. So this is an asymptote. Notice the presence of the b in there, and that's why it was important that I mentioned the b over here. This relationship, where does b come from? Comes from this relationship. It's dependent on c and a. But it also shows up in our asymptote, and when we go to graph these, I'll show you in the next slide here. We're going to use this result to do a graph. So here's our first example. Okay, first thing is get it into standard form. I'm going to divide by 9. So that shows me that a squared is a 1, and b squared is 9. A is 1, b is 9, or sorry, 3. So now from the looks of this, since the y term is positive, you know it's transverse along y-axis. Okay, and we have, of course, we can also see that the center is still at 0, 0. So let's start drawing it. We've got the center right here, and the A is the distance to the vertex from that center. So we come up, there's one vertex, come down, there's another one. Now, the asymptotes, this is where the B comes in. Now, let's see. I gave it another information on the last page that I was looking at this form. If we solve it the other way around, in other words, if we have transverse being vertical, which is what we have right now on this example, if you solve that, you're going to find that your asymptotes as x goes to infinity. Actually, it's x plus or minus infinity. It really doesn't matter. Okay, x goes to plus or minus infinity. This time y will be heading to plus or minus ax over b. Okay, so there's a little difference with the transverse. So this is the case that we're going to have in our current example. So we know that our axis asymptote y is going to be plus or minus a over bx. Well, we can see that here. We get plus or minus 1 over 3. So if I were to draw that line in, and it has to cut through right in here, it would come out like this. Roughly. There's one side of it, and here's another one. So what we typically do is we just draw a little box in here. To help us with those two lines. So we draw the box first, and then we draw the diagonals of the box. Then you take this curve and you start it heading out that way. And likewise, one of them heading out this way. So one and another one heading out this way. So we get two, depending on how neat you can draw, you get two pretty good estimates of what the curve looks like. I know this one, that one's a little bit sloppy here. This one. Let's try to make that a little neater. Coming in like that. Okay. And of course you have your foci, which really don't help us to make the drawing, but you can find them because we use our relationship. It's a squared plus b squared is c squared. So you can see that c is going to be the square root of 10, right? 1 and 9. Okay, so that's it for 10, and it's about, I think it's about 3.2. So up in here at 1, 2, 3, about there, you can focus. Another one down here, that's your focus. Okay. Okay, let's look at this next one. This time, we've got a little bit of work to do here. Let's see. It looks like one of those that we're going to have to put into standard form by completing a square. So 9x squared plus 54x, and then I'll write this as minus 4y squared plus 8y plus negative 78. And I'm going to factor out that 9 and then factor out the 4. And then complete those squares. So I'm going to add in a 3 squared here, and I'm going to add in 1 squared there. Make sure you add in 181 over here, and then you subtract the 4. So that gives you 9x plus 3, 4 with a y minus 1 squared. And this right-hand side will bring us down to negative 1. Okay, so I don't want a negative 1. I'll switch the signs on everything. I'll write this as 4 like that. And then see, this is a little odd to have it in this shape, but you can think of that as a 1/4 underneath. That's a square there. Okay, so now we can identify, first of all, your transverse axis is the positive term, and that tells us that the a squared is a 1/4. So a is 1/2. B squared must be the 1/9. B is 1/3. Okay, as long as we're at it, we must find the c. It's the square root of 1/4 and 1/9, which is what? 36, 9 and 4, 13 over 6. Okay, so that's going to be about it's not very large. It's 0.6. Okay, so let's look at what this comes out on our grid here. Okay, so this looks like the origin here. We have our center's been translated, so it's -3, 1. So that would be, if I make this a -3, there it is, there's the center. Okay, and so this one travels in the vertical direction. It's transverse to the vertical, and the A is a half, so it's only up here that I get that first one of the vertices right here, and another one that come down. Oops, lost my center. And then you're going to come down a half, so put you there. Stay, okay? And so let's get a little bit messy there, but okay. So now I'll use the 1/3 for my B value, construct that, which is going to be 1/3 about like that. It's about 1/3 over. And you can draw in your asymptotes. Notice I don't really even need the equations of these to draw them in. And then let's go ahead and just draw that in like so. And there's another one in here. Comes in kind of sharp. Heads out. Gotta be neat to get that. Okay, so doesn't look like much. And yours, the C value is 0.6, so your foci would have to be that negative 3, and then you'd have that 1 plus or minus the 0.6 approximately. So you'd have one of them. It's not. It's right in there. Pretty close. 1 plus 0.6 is. I mean, remember that this distance was only a half, so it's really close in there. You can hardly see it. The way I got it drawn there. Okay, but this is technically our location for those. Not necessary for the drawing, but and of course, if you want those equations for the asymptotes, we can easily get those too. We might as well do that as long as we got it all here. Okay, so you don't have y, but you have y minus 1 equals plus or minus. And remember, the a was the vertical distance, so we have that a was the 1/2, and b was the 1/3, and you have an x plus a 3. Okay, so you can leave it, well, I don't know if you want to leave it like that, but this would be plus or minus 3/2 with an x plus a 3. You can leave it like that. It's probably good enough. It shows how it's really just a line. It's been translated over to -3, 1. Each one of those 2 lines has been translated, and the slope is 3/2, plus or minus 3/2. Okay, I think there's one more here. Okay, find the equation of the hyperbola. This is all the information you have. So, let's see what this looks like on the graph. Just to get it straight, 0, 4. There's one here, and there's one down here. Okay, if those are the vertices, then you automatically see that this thing is transverse in the y direction. Okay, so in here, we know that the A is going to be a 4. Okay, now question is, what is B? Because remember, our asymptotes are going to involve this form y equals plus or minus, in this case, whoops, that would be an A and it's going to be this form a over b times the x because it runs right through the origin. There's no translation. The a is the vertical change, a over b, so it's heading up this way with the slope of a over b. So I have to get that b in order to get that rectangle in here, and then figure out what this thing looks like. Then I can write the equation for it also. So you need the b, but you can see in here that 2 equals a over b. Okay, disregarding the signs. But the a is 4. We know that. So b must be a 2. Okay, so knowing that, then we can write our equation. We know it's x squared over, whoops, that's not an x. Let's see, that is y squared over 4 squared minus x squared over 2 squared is a 1. So, and we're almost there. I'm just going to write this then as y squared over 16 minus x squared over 4 is a 1. And that's all you need. They didn't ask us for anything else, so if you want, you can put this graph back together here. It comes out at 2 here, so here's that rectangle. With the diagonals to help you get that sketch. And that's out like that. Okay. So that's, I think, all we're going to do on this one. I wanted to say something about that last problem with the arc length. Just we're going to, as a way of reviewing a little bit, just a little bit. There's another example on here, and let me see. Let me get that for you. Okay, here's the problem. Back here. On here. Okay, there's our problem. You can find the arc length for this one. So you don't really need a picture, but of course we could get one, and we should, I guess, maybe just practice a little bit. Just this is y squared equals 4x. So you can see p must be a 1. It's going to open to the right. Vertex is at the origin. 1 unit over is the focus. 1 unit over this way is going to be your directrix. So you do have, and it's a 4, so it comes up 2 units that way. It's going to look like that, and down like that. And you want the arc length 1, 2, 3, 4. So I guess it's 4 for the x also. So maybe I come over a little bit more like that. Okay, so that's what you want right there. Okay. All right, now, so that's the piece that you want in there. So run while here, and you want arc length in here. So you set it up. S is integral from 0 to 4. Now, either way, for x or y, it's still 4. 4 times 4 is 16, and y is 4, x is 4. So there it is, and you want the square root of 1 plus the derivative squared, right? Y prime squared. And I'll write this one for dx. So, although it might be better to do it the other way. In other words, I mean, the limits are the same, but we would have this x prime squared dy. And it's just coincidence that the limits are the same. So either way, I'm going to go with this one, 0 to 4, because it's already in a nice form here. With x is just 1/4 y squared. So x prime is 1/2 y. So when you put that in here, you're going to have a 1 plus y squared over 4 dy. That's going to give you 0 to 4, 4 plus y squared, and a half. That 2 will come out here. There's a problem with this one because we really can't integrate it, but you could use the result from the textbook to do it, to get the closed form for this one. There's a result there you could use. It's an interesting integral because when you start off, you're going to need, if we're going to do this by our method, you're going to need that u equals, sorry, not u, but y would be that 2, was it 2 tangents? What's that? What's our substitution for that again? I guess it would be 2 tangent theta. Okay, that would be our substitution. And that would lead you down to an integral involving a secant cubed. Okay, with limits of its own, which requires integration by parts. Sorry, yeah, integration by parts. So eventually you would get to an answer, and the answer is 2√5 plus natural log of √5 plus a 2. A lot of work, but just we're not going to go through that. But if you're interested, you can, and you can always double check your work here. You can use your calculator to approximate this thing, and then compare it to your numbers over here. So that's about it for that.